Welcome to EDU World Space.
So a reminder, if you take a distribution and change variables, the distribution for that new variable will be different from the original one. So being a little bit careful, you can write the spectral irradiance function developed by Planck in terms of frequency instead of wavelength. And although this distribution looks similar to the one based on the wavelength, that is, it has a peak and goes to zero at both infinity and frequency equals to zero, do note that it is a different distribution. So we can note that the frequency comes in with a positive exponent, both in the numerator and the argument, the exponential, in the denominator. However, the spectral irradiance still has a maximum at some frequency. We'll call it frequency max. And that frequency symbol, by the way, is a Greek letter nu, N-U. Yeah, so it's a new variable. Yeah. So we're going to take the derivative of this with respect to that variable and set it equal to 0 to find the maximum, just like we did with, you would do if you had the Planck function as a function of wavelength. This one, however, is a little bit easier to do because you have positive exponents in places where they were negative before for the wavelength. So again, we're using the product rule. So we'll take the derivative of the numerator, multiply by the denominator, and then take the derivative of the denominator and multiply by the numerator. And that will involve the chain rule in a couple ways. So we then have to take the derivative of the denominator, which is the exponential function. But then we also need the derivative of the argument to the exponential. So yeah, the denominator usually is the problem. And we see that there is a positive root to this. It may not be easy to find. We may need to use a numerical technique, so we'll go through that. But there are some things that will cancel nicely. 2 powers of the frequency will cancel, and also one of the powers of the denominator will cancel. And so this will leave us with the equation, let's see, 3 over b is equal to, let's see, nu over t, e to the b nu over t, and then some things in the denominator. Again, what I will do is a couple things to figure out where the maximum is. The first thing to do is kind of the short wavelength or high frequency limit. Is the first thing we'll do. And what that will do is set us up for a guess for this hard to solve equation that can only be solved numerically. So use as a guess and do an iteration, we'll get to that, to solve more exactly. more precisely, more accurately. We'll just say more accurately for the time being. That may not be the best use of the word accurate. Okay, so let's take step one, the high frequency limit. In that limit, in the denominator, e to the b nu over t minus 1 basically approaches e to the b nu over t. And we can simply solve the above. 3 over b is equal to nu over t. And I should have stated what these constants were. They are not fit parameters. We know precisely what they are. That a is the constant h, 2h over c squared. If you want to know what that value is, it is 7.37. 2 times 10 to the minus 51 using the latest data on constants available at the National Institute of Standards and Technology. And B, of course, we know that as well. It is simply h over the Boltzmann's constant. Planck's constant over the Boltzmann's constant is equal to 4.799. I'll keep a few more decimal places, seeing that it is the precise thing we need for our guesstimate. And units of Kelvin times seconds. Well, kelvins per hertz is probably a better way to write that. Okay, so using this approximation, our first guesstimate is 3 over b. So you want to invert b. And multiply by 3. And you get 6.250986 hertz per Kelvin. Okay, so that is going to be our guess. Now, to work with this, I'm going to rewrite the derivative. What to call that? The star equation. Why not? We're going to rewrite that in terms of a variable. We'll just call it x. And it is essentially the nu over the temperature. That's the important thing that we're trying to solve for. Rewriting that equation using that substitution, we can write it in a nice form. It is x is equal to 3b e to the bx minus 1 parentheses divided by e to the bx. And simply what you do is an iteration procedure. So what you do is you put in as your first guess put in your guess, recalculate x with the new x. Okay, and then so what we're doing is recalculating, and then use nu x back in the right-hand side and repeat until the left-hand side equals the right-hand side to whatever precision you want, however many decimal places you can stand watching this go on. So this is easily done with a spreadsheet in Excel, for example. You just copy and paste the result into a new cell, drag down the calculation. It will create a new value for you. I could share the results, but I don't think it's too interesting. But it did converge fairly slowly with that first guess. We were quite a bit off, and probably after about 10 iterations, we settled down with the following. And I did keep it to quite a few significant figures. Basically, Umax over the temperature wound up to be 5.8789259. Of course, it would have settled down without all those significant figures. Okay, so notice that is, quite noticeably different than the initial guess, which was 6.5-ish, 25-ish times. Oh, I left off the exponent on that. That was not good. Okay, that seems a little bit more reasonable. Yeah, so the final answer is quite a bit off of the original guess. But we did settle down to a quiet value. Now let's take a look at the sun. So we're going to actually do a case example. It has a peak wavelength from the wavelength irradiance of about 500 nanometers. Maybe a little bit off of that. We'll say approximately 500 nanometers. What about the nu max? The nu max, the frequency maximum, is the temperature. So we'll write down the temperature given for the sun is about 5,800 Kelvin. We'll give it a few more sig figs. Multiplying that 5777 by our value from the accurate algorithm will give us the maximum frequency in hertz. And this winds up to give us 3.396 times 10 to the 14th hertz. I think that's enough sig figs. Now, what wavelength does this correspond to? Okay, so that's an easy one to determine using x equals nu times frequency. Sorry, not nu times frequency, nu times wavelength. Yes. And using 2.998, so we'll keep to 4 significant figures, times 10 to the 8th meters per second, and divide by 3.396 times 10 to the 14th per second. We get a wavelength of 883 times 10 to the minus 9 meters, nanometers, in other words. And notice that this is quite different from the peak of 500 nanometers. In fact, this is in the infrared. So whereas the peak wavelength is in the visible spectrum, the peak frequency, which governs the energy, since a photon has an energy equal to Planck's constant times frequency, that energy is in the infrared part of the spectrum.